Welcome everybody, it's Dr. Brizendine. I want to welcome us to our class session. A couple things. First off, I want to introduce the schedule, which we've not had, but we do presently have. Let's take a look at that. So what this will consist of is our readings for the class. And as it states there clearly, these readings are not optional. In fact, they are required and the content could appear on our final exam. So what we have is an article from FRAC talking about basic integer overflows. That could have easily been week 2, but it's not. It's week 3. So review at this point. And we continue along in or start in our Gray Hat book, chapter 2, and then the Shellcoder's Handbook selections, or a selection from chapter 18. So go ahead and check that out. I also wanted to announce to our students that I did receive email confirmation today that the president of DSU has signed off on the creation of the Verona Lab. So this is a lab that specializes in vulnerability and exploitation research for offensive and novel attacks. So the Verona Lab, it's kind of a brother lab to the Madrid lab, both obviously named after major European countries and focused on reverse engineering, but with very different applications. So what Verona Lab does is it specializes in research, vulnerability research, software exploitation, software security assessments, as well as developing cutting-edge tools and techniques that could be utilized for software exploitation. And that's really kind of the crux of what my personal doctoral dissertation was, which resulted in the JOP rocket, and that saw it being part of DEF CON last August. So right now the Verona Lab is still very new. Ideally, this will get clients or customers to fund security assessments, whether looking at binaries or source code, to try to enumerate vulnerabilities and then to see if exploitation is possible. So that's one thing in the future, and that's really driven primarily for students, and they'll be mostly on-campus students, I would imagine. But things do move a little bit slowly in the academic world, and so I'm not sure when we'll actually get clients. So that likely will not be this semester. Of course, funding from different government agencies is a possibility, and also just simply the development of new tools, new ideas, refining things. So in that respect, it can kind of be a think tank. The goal there is just pure research as opposed to monetized application of that knowledge. So I do have great hopes that the Verona lab will be of great benefit to the DSU community. Much as some of the other labs, such as Madrid, have greatly benefited DSU. And Madrid has brought some great speakers to DSU, both on campus as well as remotely. Some of them even doctoral students. So who's to say what the future could hold for the Verona Lab and the research that could develop in the future? I think it could be very, very interesting. But with that, I think we'll continue on with some of our slides, finish up with talking about C, and then on Thursday, we will get into our next segment of activity. We'll start with some fuzzing, some discussion of that, and learning about some of the tools that can be of use to us in that respect. So we will go back one there. So revisiting sign extension, something that of course is fairly important, fairly significant. Sign extension is a vital and essential part of the C language. Some perfectly legitimate, valid purposes. If we need to do integer promotion, we want it to be sign preserving if it is appropriate. That allows us to maintain the sign bit. The sign bit is going to be the leftmost bit, either 0 or 1, indicating whether it's positive or it's negative. And of course, this is done whether you're doing a typecast, you're doing assignment, you have a function prototype, and it calls for a sort and you're feeding it an integer. Whatever the case may be, we're trying to preserve the sign. Unfortunately, of course, and there's always an unfortunate aspect of it, but sign extension can create problems for us too. And this comes into play when programmers may think they know what's going on, but they may not consider the ramifications of doing a typecast. So specifically, what that means is you have a negative value that is assigned integer, and you do a typecast to an unsigned integer. You might think, oh, it's just going to remain negative. We don't think about it being negative, or we think it'll somehow convert to a positive number. And it does convert to a positive number. It just happens to be an extremely large one, close to 4 billion. So in those cases, that can sometimes induce a buffer overflow, which certainly, to say the least, is problematic. So we have this example here of some code. So what this is that it goes and checks. You could kind of view it as an array of domain names delimited by zeros that is delivered over the network. So we get this array consisting of domain names that are delimited, and we want to do some checking on it. We're trying to avoid a buffer overflow, but unfortunately there's some problems with the code, some issues that prevent that from being successful. So we have a check right here, and that check is it's checking to see, okay, am I between or rather am I below the maximum amount? And the car array, or the car pointer there, indicates that it could be 256 or whatever characters, so falling within that range. But what we may not consider, though, is the possibility of what happens if that value happens to be negative. Why do we care? Well, we do care because if we do the Sterling, as you see right there, on name string, that's going to return a size t. So that's effectively an unsigned integer. So let's say, hypothetically, that we enter this, and the result of having our Sterling is 5, and count is a -1. So what we'd have then, effectively, if we go through this, is we have the 5, and we have 5 because, well, that was the input. And then right here, instead of having -1, we have this colossal number, 4 billion something. And the reason why is compatibility. This right here is size t, unsigned integer. We need to convert that to size t. And you might be thinking, okay, so how would this be possible? How would this be less than max length? Well, the answer here is numeric overflow. So it could be possible to have the values be so large that you would instead cause an overflow to occur, and you end up with, small values such as 3. So it would pass that. And what comes into play next here is this right here. And you might be thinking, well, we have the in there, so it must be safe, but actually it's not safe because we use the count here to tell us the size. And we have our count as -1. Okay, so -1 is problematic because, again, it makes it this huge 4 billion type number, which then causes an overflow to occur, unfortunately. So that's how we can have a buffer overflow situation here because of problems with sign extension, problems with numeric overflow. Now, this is a somewhat subtle issue. If you're not providing it with malicious input, it's going to run just fine. But when you do start entering malicious input, then some of the shortcomings become more readily apparent. And this is something that, a compiler is likely not to throw up any kind of warnings about. So there was then an attempt to fix this code, because this is a real world example. So they tried to fix it, but unfortunately it didn't really work out too well. And how they tried to fix it was by doing unsigned integers to cast it. So we would get this result, cast it, get this result, cast it. So that would avoid the problems, right? Well, actually, it turns out it didn't do a single thing, because what was happening was this was already implicitly happening. So now we're just doing it explicitly. So no difference whatsoever. The count would be typecast to the same, so we provide it with a -1, and now it's 4 billion. And if we can manage to cause a numeric overflow situation to get us past this point, then we can get down over into here to the string cat and get our buffer overflow situation over here and take this and overflow that. So operators like the addition operator can already implicitly do some of that. So really nothing whatsoever changed. The secret is, get the right negative value to send it over, and have everything else tweaked so that we can bypass that and then cause the overflow situation there. And again, those are real world examples. An attempt was made to fix it, but there was some misunderstanding of the issues, apparently. You would think that they would, test a negative value, but what they probably did is they probably tested a negative value, but that negative value, for whatever reason, didn't fall into this situation here where you'd have the numeric overflow going on there. So they thought that they had fixed it, but they actually had not. So some pro tips, some things that we could work on. Now the fact is, a lot of developers, when they use things like shorts or small signed integers, they may not anticipate the fact that they will be sign extended. Sometimes when that happens, there are security implications. Other times there are not. Now, if you're looking at the source code, that can be difficult, a little bit tricky to discover. But if we check it out in the disassembly, we see that it utilizes the move SX or move ZX mnemonic, so we can explicitly look for that. Does that mean that there are security implications? No, but there could be. We would need to evaluate it a little bit more carefully to see if there are security ramifications. Is it a situation that somebody could take advantage of? That simply may not be the case. Input, of course, is going to be an issue. Even if there are security implications, if we can't reach it And if it doesn't have any effect on anything else that we're doing, then it's not really useful for our purposes. So for sign extension vulnerabilities, some things we could focus in on are short integer values, the shorts, or the pointers. And a lot of times we'll see those present in code that deals with a lot of network activity, particularly if you're having to deal with length being specified. You can also look for code that makes use of a short or a char, and try to see if there's a situation where it's being forced to be converted into an integer. You know, could we have, if it's a signed char or a signed short and it's a negative value and we get it forced converted into an unsigned integer, well, then that could become a very large positive value, which is a recipe for disaster if you're dealing with something like a buffer overflow that could result. Truncation is also deadly serious. This one, thankfully, is not something that typically happens. This is often the result of poor thinking, carelessness on the part of our developers as they fail miserably at considering the issues of arithmetic conversions or integer promotions. So unless somebody explicitly causes the casting to occur, whether they're doing a type cast, maybe they have a function protocol that is using, that calls for a short and you feed it an integer, that is going to force it to happen. You know, if we're doing assignment, which our lovely example right here is an assignment, those all can cause truncation. So let's work through this example. We have int var a, dead code, and we have a short called duh, and then we do an assignment here. So duh is now equal to var a. So what we do is we chop off the top 16 bytes and we're left with code. Pretty cool. So we have a real world example here of how truncation or truncating vulnerability can come into play. And this sets us up for a buffer overflow situation. So it can be very, very serious. So we can walk through what's going on here. We have an unsigned short. So unsigned again means there's no negative value to it. And we have a mechanism to a char pointer, a mechanism to get user input. That user input is then stored there. And then we have a string length. And then the result is stored in an unsigned short. And even though it's unsigned, it's going to use the size t, essentially an unsigned automatically right here. And so what you could do is, what if you put in something like 66,000? So in that case, truncation would occur. So the truncation result would be 464. We have a check here for the size, checking to see if that is going to be able to accommodate the buffer, and 464 will be able to pass that. And the reason why, of course, is because it's less than this value, so we don't have the program die. So then continues on to stir copy. At this point, we copy the value, so the user string is then copied over to myBuff right there, but they might be thinking, that this is the same value as the short. We had our testing there, but we did the testing on the short. The short truncated the 66,000. So in this case, we have 66,000 that is going over 1024, causing a buffer overflow situation. There was an effort at security. It was just poorly thought out because of misuse of appropriate data types. So sad, sad situation indeed. Auditing of truncation, some things that we can look out for here. Anytime we encounter having an integer value being assigned to The smaller data types, the shorts or the cars, we want to watch out for that. That's a possible area. It doesn't guarantee that it's going to be problematic, but it could be. We can look for areas where shorter data types are used for things such as length or the results of some calculation. If we find them, then we want to trace backwards and see that if is there any place where truncation occurs as part of this. So look for the short or shorter, because it doesn't need to be short, it could be a car. They're both integer types. So find those and then backtrace it to see if truncation leads us to that state. Take a look at our structure definitions. We will find that sometimes they may call for a short in the structure, but what happens if we're feeding it an integer value instead? Then truncation will occur, and as we can see, that does occur with network-based code from time to time. Sometimes it's the result of programmers just not really thinking things clear as thoroughly as they should. They might think, okay, now this value should be within the range of 0 to 100. Okay, a short can accommodate that. I'm not going to waste memory on an integer when I can use a short, so I'm going to use a short. But they may fail to consider that somebody could intentionally or unintentionally have a value to cause truncation. Some people just are not security minded, and so they might think I'm going to be more efficient or more eloquent with my code, and that can result in some undesirable problems, unfortunately. Comparisons is another area that can lead us to grief, to trauma. So if we have comparisons of integers of different types, that can lead to security issues. So different types, the compiler will automatically perform is necessary first integer promotions and then the usual arithmetic conversions on all of the operands. Now these are going to need to be compatible types. So it's going to be converted to something that's compatible across the board. Potentially, that sometimes could lead to changes of value. Could be due to the sign being changed, whether from integer promotions or conversions. So we may have, a good classic example is, if we have an unsigned integer in there and we're forcing something to be changed to unsigned, that could cause something going from negative to a very large positive value. So if we're not cognizant of that when we make that comparison, that could be a serious issue. As a security auditor, somebody looking for avenues for software exploitation, that's a wonderful area to explore. Very subtle, that somebody may not consider or could easily miss, particularly if they're using more traditional input rather than the aberrant input that we as exploit developers would be more wont to use. So looking at unsigned integers and comparisons is something that could be good. Another issue to consider is, are you checking for something that is impossible? If we have an unsigned integer and we're checking to see if it's less than 0, well, when is that going to be possible? Never. Something like that you could maybe get a compiler error on, but you may not if you do less than or equal to, because part of that is possible. It could be equal to, but there's also the possibility that part of that may not ever be true. So some logic errors could come into play to bite us. Operators behaves much in the same fashion as with comparison, where they may have results that we may not anticipate. If we have something that is unsigned and we have something else that is signed, then there may be some conversion going on that we may not be thinking of, causing things to go from positive to negative or vice versa. And this, you know, all of this happens automatically. It's implicit. So if we have values that are or data types that are not the same, they need to be converted to become the same. And as before, we follow the same behavior. We follow integer promotion and we follow the usual arithmetic conversions to ensure that that happens. So understanding some of those rules that govern these operators is certainly useful. And what are those rules? Well, essentially it's just following integer promotion, following usual arithmetic conversion to help us guide how operators, how they work. Because people may not think about that, they may not consider the possibility of some of these unusual results that could transpire as a result of crossing the boundary from positive to negative. And for us as exploit developers, that is great news because we can definitely make use of that. Size of operator, we've kind of alluded to this before. It is something that is fairly often used for things like buffer allocations, checking parameters for length-oriented arguments to functions, size comparisons. So pretty regularly used thing. Um, and so that, we've mentioned some of the size t issue, how that can come into play. Some other things as well is what happens if we use it on a pointer instead of the target of the pointer. So pointer is size 4 bytes. Some people may try to use it to when they mean the entirety of the buffer, but it's gonna just, if you just do the pointer, well, the pointer is only 4 bytes. So you may be anticipating a different result. Now, in realistic terms, this is maybe going to be less useful to us because a lot of times, if this involves memory allocations, it'll be caught fairly early on because you'll have a crash. If it's expecting one value and it gets a completely aberrant value that's going to cause a crash. Now, that's not always going to be the case because there could also be some code paths that are less common that we may not have explored. Maybe you need to go and do something very specific within the program in order to reach this code path where this particular size of makes use of a pointer incorrectly to potentially lead to a situation that could be vulnerable and be exploited. Some tips here for auditing comparison, what we can look for. We want to focus in on comparisons that are close to memory allocations, to the indexing of arrays, or copy operations. And if we encounter them, we can't just glance at them and say, okay, this is bad. I'm done with you. I'm going to put you on my list of things to exploit. It's not that simple. We need to look at it line by line, evaluate it, and consider the possibilities. Look at the relevant expressions. Is it something that could be made use of? Maybe yes, maybe not. Another tip you can do is to keep track of each variable as you encounter it and the data type. What data type is it? You may see that it is a particular variable may be an integer, but maybe it's used elsewhere as a short. So we could have some kind of truncation that may be going on. And additionally, we want a lot of what we do with reversing, whether it's malware or software exploitation, involves some degree of tracing from point A to B to all the way to Z. And as we go from these different points, different ranges of values may be possible at certain points. At point B, certain range may be possible that is different from point C. What is acceptable? Um, Maybe there's a very specific place in the code path that we can reach that could cause an exploitable situation, but other places there just are no issues. We can also watch out for unsigned integer values that may cause other operands to be promoted to unsigned integers. Size of and Sterling are some great examples there. So if we have a comparison and we have these being made use of, well, then we're going to cause this integer promotion to unsigned integers. And that may have, if there's a negative value, that could have a very interesting result, as we've kind of already explored a little bit before. So let's take a look at the size of vulnerability. So we have size of being used incorrectly on buffer. It's always going to be 4, always 4 bytes. They probably think it's 1024, but that's simply not the case. Now, if the style is present, which that's what this is checking for, then it will then go into this situation right here, and it will end up causing an integer underflow condition and the size argument to sprintf. So right there, we would have the integer overflow situation. So explaining that, we have 4 minus Sterling buffer. So the buffer is going to exceed that amount, and so then that would be a negative value, but it's actually a size t, so that would then change it to a very large positive value, causing a buffer overflow situation there. Kind of sad. They're even using the end there, trying to making an effort at being more secure. Whenever you see people using the end there rather than just the endless version, you have to applaud them at least for their efforts. But unfortunately, those security efforts were insufficient. Okay, so auditing size of, we want to look out for the use of size of, where the size of a pointer to a buffer is used, and anticipate, are they actually looking for the size of a pointer, which is 4, or do they mean the size of the buffer? So very subtle difference there. If there is a size of being used in expressions, we would want to consider where operands may be converted to unsigned values. So I would check that out. And if those are found, then we would want to look at the functionality line by line and try to figure out, again, is there a security issue? Just because there is a size of doesn't mean there's a security issue. It could be perfectly benign, perfectly 100% secure. You know, we need to apply our critical thinking skills and just check to see if it's possible. Signedness with operators. So this can come into play in a number of different respects. So comparisons, right shifting, division, modulus, all of these may produce unexpected negative results when they're coupled with signed operands. So the right shift operator is one, and that's the right shift operator. Now, right shifting and left shifting is something that happens automatically a lot of times with a compiler if we use multiplication or division and involves powers of 2. We can also explicitly use it in our C code to do much the same thing that the compiler might do on its own. Why might you do it? Well, it's faster, it's more efficient, it's more computer-like. So if you, as a good programmer, can recognize that and see the opportunity to do a right shifting instead of simple multiplication, then as you evolve to the more superior programmer being, then you might do the right shifting instead. Um, that can also create some problems though. So people might think that they're being, I don't know, elite or sophisticated, but if they're not using it as smartly as they, or smartly even a word, I don't think it is. There goes my intelligence. So if they're not using it as well as they should, that can create some issues. So if we use the signed integer as the left operand, then when you right shift a negative value, then the sign of that value is going to be preserved by the machine. And it does that by sign extending arithmetic. So whether or not that's the correct or incorrect behavior really depends on intent, what the program is trying to do. If the person is fairly cognizant of the ramifications of doing that to a negative value, then maybe it's fine. But if they're not and they're expecting one value, then they may be surprised at the value that they get, because it could end up being a very large value potentially. Um, Now, this is something that can be more tricky to find if we have the actual source code, but if we look at it in the disassembly, well, it's a little bit easier because we can see the specific assembly mnemonic. So SAR, SAL rather than SHR or SHL. So it's going to be more prevalent with right shifting rather. So if you encounter this type of thing, then that's a potential opportunity. So right here we see right shifting vulnerability. Let's explore what happens here. So the number here, there's our number, is intended to print the high 16 bits variable. So that's fine if it's a positive value. What happens if our number here is negative? Well, it's going to extend that number by 16 bits, so it'll become a very large number. So in this line right here, we have a situation where they can come into play. So we have the format use specifier, and so that's going to cause the result to be unsigned. So right here they go and get the buff, they get the size for that, whatever this is, and they provide for that right there. But then because of this right here, we're making this sign extend. So we are doing this one right here. And so this will become a very large value, and that will then cause an overflow situation right there. So a little kind of subtle thing that, if you're just looking at your code and you're not thinking about it, you might miss out on that. And you may do a little bit of testing, but if you're not providing a negative value, then, well, you may not encounter it, and you might think, it runs perfectly well, there's no issues, but actually there were. Division vulnerability, so somewhat similar. I don't think I guess I do have an example. So one of the operands here is negative. Obviously that means the quotient is going to be negative too. That's simple math. But even though we may consider that simple math, applications may not consider the possibility of negative results when performing division on integers. Okay, so let's see how that comes into play here. So we're getting some input from the network. We get sockfd, we have a bit length, we make that an integer, and then we go and get our length from the network. That is then provided to us. We have some allocation going on. We do some malloc there. We have bit length, we're dividing it by 8, so we get it into bits, and then we have a +1 in case there's some extra stuff. We can take care of that, and then we can address that. But well, the vulnerability here is we have this adding going on. If I can make this into a -1 somehow, so if this is 8, maybe I get the input to be -8, and look, oh, I have a way to influence the input, so I make this -8, so that turns out to be -1. -1 plus 1 is 0. It'll do the allocation of memory. It won't be 0. It'll make it as small as it can, but it will do an allocation. Um, and then that also comes in play over here with read. This value right here is the same as before, -1, but the parameter there is size t. So instead of -1, it's going to be 4 billion something. That's way too big. So we have a buffer overflow situation going on right there, because the buffer here is as minimal as possible, and we're providing a character size of 4 billion or whatever. So division vulnerability can be very real, but it can also be something that's very subtle that you just kind of have to work through. Modulus vuln operator is something else that is very similar in nature. It can produce negative results if the negative dividend, if there is a negative dividend operand. I don't have another example just because it's same concept really as division. It's just slightly different. One thing to note is that modulus operators are often used with arrays that are fixed size. What are fixed size things? A hash table could be something. So we could have something that is written to a hash table, negative value. It sits there in the hash table and it's not used right away. But eventually, at some point, it would be used. And then, similar situation to what we saw right here could come into play. So some auditing tips. Keep in mind that with right shifting and signed operands, so sign meaning of course it could be positive or negative, then we potentially could have an exploitable condition if there is, if we see, a SAR or IDIV. So much like with right shifting, when we do the sign extension or signed division or dealing with signed values, there is a specific assembly instruction for that. And in that case, it's IDIV. So if we do signed division, it's IDIV. If we do unsigned, it's div. So if you're looking for the potential vulnerability there, then we could look at this area right there. It's the IDIV area. So we check that out. So, if we're doing auditing and we have division, we have some right shifting going on, and we see signed, there's the capacity that we could supply it with a negative value, which maybe not, could lead us to an exploitable situation. Other things to consider: typos, omissions, impossible situations. Going back to the comparisons, what if we're looking at a situation that is just impossible and feasible? It'll always happen one way. Well, guess what? The compiler will take note of that, and it may just treat it as dead code. So such and such will always happen. The comparison may not even happen. And when you are in the comparison, this is something that really experienced developers can fall into. They think they're elite and they have many different conditions going on, and they just omit some parentheses as part of the comparison because they think they understand the logic and it's just not necessary. But instead, it causes the comparison to be evaluated in a way that they don't anticipate because of the lack of the parentheses. Instead of actually checking for a condition, it makes it always true or it makes it always false. So that's something to look at, particularly at a source code level. Now, when it's compiled to binary, the comparison may be present. It may may be doing that comparison even though it's always going to be one way, or it may omit it. It may be the dead code issue where it's just gone. I don't want you to think necessarily that it's going to always be this situation. Sometimes it will be there even if it is redundant. Um, so taking a look at the actual logic and evaluating that mentally to try to figure out the possibilities, much as we've talked about before. So we have a real world example here. We have Boeing 787 numeric overflow to the rescue. So there are numerous examples out there like this where silly software programs could cause catastrophic things to occur. And this is potentially catastrophic. This is the result of numeric overflow. So speculation is 248 days continuous power causes 2 to 31st centiseconds of continuous operation, which comes out to 248.55 days. Essentially, it's integer overflow. You're having something running continuously for that period of time. They did not consider the possibility of signed integer overflow. And so we might think, well, big deal. Who's going to leave their plane running continuously for that long? Well, my response is, I'm not a pilot. I don't operate planes. Maybe there are some things that they just leave them on continuously. So maybe that is a security issue. Maybe it's not. But there could be other sources of power that could be AC, electrical power, in there. There's probably not just one because a plane is pretty big, right? So apparently there's 4 of them. So if all 4 of them were going simultaneously for 248 days, then all 4 of them could fail, and when it fails, it goes into fail-safe mode. So regardless of whether it was flying or not flying, then that could be a very catastrophic situation. So fortunately, this is something that they caught. They realized that this was an error. And again, I don't know about airplanes, okay? So maybe it's a very improbable situation. Maybe these things are not left on that long. Who's to say? And even if it is very improbable, there's always, the off chance that, some moron, some idiot out there, maybe some foreign country, cheaper airline, maybe they decide it's going to be easier or cheaper just to leave these things running, or some extraordinarily lazy person just behaves inappropriately, and then for whatever reason that could get us to that situation where we would get the 248 days. There may be rules and regulations in place, but these people decided not to follow them. So we need to consider all possibilities with things like this. Pointers. Pointers is a vital part of the C language. So a pointer points to an actual physical location in the virtual memory. So there would be a specific address associated with it. Pointers are implementation dependent. They're similar to unsigned integers, presenting values as such. If you subtract them, the result is going to be a special signed integer type. So that's kind of cool. We can have things like pointer arithmetic going on, but if you do that type of thing, the compiler is not going to check to see if the results are valid or not. So you got to be very, very careful about that. There's also alignment issues too. If you know about and understand alignment, then maybe you can address that. Not everybody does, and there can also be some subtle things going on that people may not consider. So we also have a little slide here demonstrating the idea that pointers can be null. So right there we have a null pointer. And then reassignment. So I have a pointer here, this is how I declare it. I have an int b, so it's an integer, this is not a pointer. And then right here I do a reassignment. So the reassignment is this now points to the address, the virtual memory address of int b. Okay, so let's check that out with printf and see what our results would be. So we have this sign right here will show us the address, the location, and that corresponds right here. So that's an actual virtual memory address. So that corresponds to endpoint R. And then right here is going to be the physical location, or actually not physical, virtual memory location of int b. And then here we have the value of int b. And that's how we would present that there. Now this slide probably could have gone with the other content that we had on operators, but it's here. So we can view the possibility of wrapping. What is wrapping? Again, wrapping means we go from that boundary from positive to negative without thinking about it. Different ways in which it can happen. At this point, how it happens is perhaps less important than the fact that it does happen. So if it says yes, it means that the wrapping can occur. So as we explore all these different operators in the C language, we can see that there is a number of them where wrapping can be possible. So this is an example here of how we do it wrong. So we have two unsigned integers, and we have a and b, and then we're adding them. This is wrong because it can induce wrapping because these are unsigned, and if the value well, I'm not sure necessarily this is unsigned. I wouldn't say this is wrapping. We could definitely have issues because if we have an overflow situation. So if I have like 4 billion here, 4 billion there, and that's close to the size limit there, we add them together, and we could exceed the capacity, and then it could go and then become a very small number. But in any case, a correct way to avoid that there is to use the limits. So this checks to see if we're getting into a situation where we're approaching the maximum, and if it is, then we can have some special error handling present there. So in summary here, specific issues to watch out for as far as overflows, underflows, those types of things. Truncation, where we can have assignment of wider data types to narrower, so we have an integer to a short. Arithmetic overflow, where the arithmetic operations may cause a value to be too big to fit inside a variable. We have signedness issues. If we're comparing a signed and an unsigned, something like a size of, and then that will then force it implicitly. We could have a signed negative become a very large positive, and then we get the result we don't anticipate. We don't take into account the fact that there's 2's complement. We think, okay, I know math, I understand math, and that's great, but we also have to consider how is math being implemented on a 32-bit program. Is the program 32-bit? Is it 64-bit? Either way, 2's complement comes into play. So you could have a very large number, then in fact become negative. So that's that for this slide. I do have another slide to show you guys. So this encompasses just kind of a broad range of different topics that are at this point in the course. It's just good to make sure that we have some common ground. So some of it's C, some of it's just some good stuff that we need to know. So stack versus heap, what's the difference? How can we visually see that? If you don't know what the stack is or what the heap is, I would invite you to do a little bit of checking up on that. But how this can come into play here is, so stack if we declare something just a regular variable, that will it'll live on the stack. So the stack is going to be specific to a function. Once that function ends, then it's out of scope, it's gone. It's possible it still may exist on the stack, potentially, the area of memory, but effectively for the program, it's gone. And if you think about it, a program is just a series of function after function after function, or things that are going to be functionally equivalent. Globals is when we want it to persist. So we could enter one function, leave that function, and it will continue to persist. It will remain. So how do we declare those? So we could have a structure here, and this is a way to do it so that it exists on the stack. We could also make it so that it exists on the heap. In this case, we need to dynamically allocate memory, and the way in which we do that is with malloc. Malloc allows us to dynamically allocate our memory. So we go ahead and we do that, and this will exist on the heap. And as we get into a program, we'll see that there's a certain range of memory that's going to be the stack. And then there'll be other area that is going to be the heap. So entirely different areas of the heap. If you go into something like Process Hacker and you explore the virtual memory of a program, you can explicitly see the stack or the heap, and that's possible with many other debuggers as well. So we have the dot operator allows us to access it from if it's stack based, and if it's heap based, then it should be an A right there. Then we use this, the pointer operator. Some memory copy functions can be inherently vulnerable, and this really pertains to these first two rather than the second two, where we don't require the size of the destination buffer. These ones right here actually do. It's an effort to be secure, more secure. And we might think, those are great. Those can allow us to be safe, and we don't have to worry about overflow. But as we saw from a number of our examples, overflow still is possible. So if we somehow can get the size input to be too big, maybe it's through careless programming, or maybe it's we're somehow influencing the user input. Maybe we're going from a negative and making it a very large positive value, or maybe somehow they explicitly even let us enter it. There's a wide range of possibilities. So it may not be safe. It also does not guarantee null termination. So null termination will end a string for us. So effort at being secure, but it may not be enough. It just may not be. This one here does always null terminate, so that can be useful. But even if you do see something like strcpy, it doesn't mean that it's inherently going to be unsafe for two reasons. One is our input may not reach it. If our input cannot reach it and we can't influence it and we can't do anything with it, then it's no good to us. Maybe it's just part of the program that uses a certain range of values that will always never be aberrant. We as the user cannot influence it. We cannot have an impact on it. So it's useless to us. Secondly, maybe they have another way to sanitize it. Meaning maybe they're looking at the source variable and they're doing a check on that to see if it exceeds a certain size, or to see if it's the same size as the destination buffer. So there could be additional code that could explicitly check for that. So don't get too excited just because we see that, because it could just be used in a safe way. And that's great. Other vulnerable functions where we lack boundary checking. much as here we lack boundary checking. So gets, we can get some user input. Sprintf, so a way to outprint some stuff. Strcat, strcomp. We could try to use some of these in alternatives, but as we saw before, it may be more secure, but it doesn't mean it's fully secure. Scanf is also notoriously vulnerable, so any of those could be opportunities. Now this is low-hanging fruit. If you see this in your code, should be one of the first things that you're looking for, whether it's binary and its signature detection detects that, or you actually have actual source code. So if we can find those, great. See if they're being used in an irresponsible fashion. See if our input can reach them. Memory leaks, those can be problematic. Something that we should certainly be aware of. May not always lend itself to a vulnerable, exploitable situation, but I think it's good to be aware of it. So this is where we have memory that is allocated, but it's never freed, and so that can have a very adverse effect on performance. So one way in which that could happen is we have reassignments. We have a couple allocations here, and then we go and reassign it, but where do we free it? So that's certainly an issue there. Freeing a parent block first, so one of those may contain pointers to other memory, and then reallocation. So reallocation is something to consider. Now if we do a reallocation, then the original one is going to be invalidated. That's what it says right there. But what if it fails? If it fails, it returns a null pointer. In that case, the original pointer remains valid, and then you need to explicitly deallocate it with free, or do the realloc so that it is successful. So if you are using realloc, are you checking the return value to see whether or not it was successful? Because if it wasn't successful, then we have a memory leak. Maybe it was successful one time, or not successful, but it was then successful on a second attempt. So some things to consider there. Use after free. Very big deal in terms of exploitation. It can come manifest itself in a number of ways. What this is we have a pointer. We address what a pointer is, and it is used after it has already been freed. So in this trivial example, we have a pointer right there, and then we free it, and then we try to use it again. So what was originally there is gone, and what can happen at this point is aberrant behavior, unexpected behavior. So depending on the situation, the operating system, the application, so on and so forth, it could just be random values. It could be the same value if nothing else has happened. If it has been overwritten, the attacker could explicitly go out of their way to intentionally override it with a value of their selection. It could be a pointer to a virtual memory address. Maybe it sets a function pointer, so it could cause a function to be run. It could be a memory disclosure. Memory disclosure could come into play for something like an ASLR bypass. Double free. We are freeing or deleting the same memory chunk not once but twice, and that can result in a write what where condition. What that means is an attacker can write what they want, an arbitrary value at a particular location. So that may potentially be the end result there. So this possibility here, we have a pointer at a function pointer. It's dereferenced at some other stage in the program We do something to cause it to be dereferenced, but what we do is we replace the legitimate memory address that was there with something that the attacker legitimately has control over, and so they place some kind of malicious code allowing them to do effectively whatever it is that they want. We have a real world example here from Zero Day Initiative with IE 11, so a couple years ago, I think. Um, so we can work through high level, how it deals with this. So heap free is going to be the API that will need to be triggered, and that will free object X. Object X resolves or resides at address A. We then cause a new allocation to take place. So if we just have a heap free one and then we have a second heap free, that's all we do, then nothing special really happens. We need to work to take advantage of that. So causing other allocations to occur and overwrite the same previously occupied location is one way in which we could do that. So we cause a new allocation to take place, allocating a new object Y that resides at address A. How do we do this? It can vary depending on the situation here. So with this particular thing, they're creating objects. So the objects would need to be the same size, and they may need to try spraying multiple ones just to make sure that we get it. Uh, what you would call this could be heap spraying. Different types of heap spraying. So you could just heap spray massive range of memory, or you could do it a more precise heap spraying. So that's one situation there. And then we go and trigger the second heap free. So that frees object Y, since Y resides at A. That Y freeing is premature because there still may be other pointers to Y that exist elsewhere. Much as before, we can then cause a new allocation to transpire, and then we have a third object that is going to now be residing at address A. So we could effectively call this object Z. We may need to have another heap spray occur to cause that overwriting to happen. So at this point, we've had two double frees, and we've overwritten it. So now we've overwritten address A with object Z, and we can now trigger code that would try to use object Y, from right over here, but instead it's going to operate on object Z, which occupies this address there that was previously occupied by object X. So in some respects it's somewhat similar to a UAF, but a little bit more convoluted. So that could be an exploitable condition there. Double fetch. So if you ever heard of a race condition, which I'm sure most of you have probably heard of it in an operating systems course, or somewhere you've encountered it. This is an example here. So we have the user mode, CPU, and then kernel mode. So value is changed in between check and then actual use. So right here we have a value that is being checked, and then we do some additional activities. Instead of using the same value that was checked and locking it, this is free to be modified. Could be changed, something else could happen to it, and so the buffer size is now changed from this value to this value, quite a bit larger, and so that could maybe cause an overflow situation since it's so large, or it could be some other exploitable situation. But in any case, the end result is we're not locking this down, and we check it, and then we instead of using it, we then go and retrieve it or fetch it a second time. Some other issues can come into play with optimizers or optimization from compilers. So this situation right here, we have a function. We get a password from a user, such and such password. It's being made use of. We connect to a mainframe. We do a memset. So we get the password. We utilize it. But optimization may, it may work fine for this function. When this function goes out of scope, then maybe it'll optimize the memset out. Maybe it doesn't think that it's necessary. Maybe it doesn't. Some of those types of things may not be considered. So some optimization could make it so that this could go away. And what happens if the password is intended to be used elsewhere? It may not necessarily be in this particular example. As I look through it more closely, it may not be relevant, but in some cases it could be relevant, where optimization could take something that could be useful, and it makes it go away. So we may not consider those types of things. Newer code patterns can create some security issues as well, particularly with very large browsers. Large browsers can be extremely complex. Modern browser could have 75, 100 DLLs. Some of them are systems, some of them are internal. Now, one way that you could try to address that is the usage of smart pointers. So the destruction then of the pointers is managed by the application. But what if they're not consistently used? Then that's going to be ineffective. And some of those code bases are so large, and some of them are well established, that it can be a big issue to go and remove and make all those changes. Use after free can be something to look for. And some things like Internet Explorer, those have already been addressed with appropriate remediation. But even if you do encounter a use after free, it doesn't mean you're going to be successful. Those can be a little tricky to get them to work just quite right. You need to have some good knowledge of how allocations work and garbage collection for a particular browser. Some of that information may not be publicly available, so you may need to go and do some reversing and experimentation on your own. Those types of things are often changing. If people recognize that there are security vulnerabilities, then they try to address those. So Internet Explorer has become much more secure. Does it mean it's 100% secure? No. But it is very, very secure with respect to UAF, so that any more that may not be an effective area to explore. Doesn't mean you can't go after use after freeze and other things, potentially, or older operating systems. Casting of complex objects, so type confusion can come into play. We could have complex objects that may be a specific type. If we have remote data coming across the network and some casting going on, what are the effects of that? As we saw previously, there could be many different effects potentially if it's not done correctly. So some examples: what is a smart pointer? What's a raw pointer? So raw pointer, right there, we need to explicitly delete something. We deallocate it. So that's how we do that here. We use the delete keyword in that case. The smart pointer, so this is on the heap. The smart pointer does stuff on the stack. So once it's no longer being used, once it's gone, we don't need to do anything. It's automatically taken care of for us according to what was set up. Some more information and examples there. We have a raw pointer. We create it. We do something with the object, and then we delete the object. Here we have a smart pointer with an object, and then we make use of some function, and then it's done, it's destroyed, it goes away. UAF, we've talked about this, so dangling pointer, an object that has its reference deleted or destroyed, but the reference not updated. So historically, these have been very prevalent in browsers, sought after. There's been a lot of remediation, so it's not as big of an issue, particularly in Internet Explorer. Chrome has really good sandbox, but they're more after kernel level exploits or escaping the sandbox. But those are much more very extremely difficult to find those types of bugs. So you need to have very high level of sophistication to be successful in that arena. So we see here example a dangling pointer. This has been freed, but still pointing to that location. We could have one object and we could have multiple pointers pointing to it. Or we could have one object and just one pointer pointing to it. So we have an object. There we go, an object, its methods. It's somehow freed, so it's gone. Then the attacker allocates a new object, so object T, but it resides at the same memory location. Now for this to happen, it needs to be, well, there could be a lot that needs to happen, but let's make this simple. At a minimum, it would need to be the same size. So if we could get that to happen, then we could overwrite this. We could override it with something that we, the attacker, have control over. So it could be a function pointer. So when we go and call upon this, then it could be some malicious function pointer that does something beneficial to the attacker. Maybe it's not that. Maybe it's a memory disclosure. Maybe we're pointing to part of a DLL function that has ASLR on it, and so we can then deduce from that the base address. And with the base address, then we can effectively have a bypass. Which, don't worry if you don't understand all that. We'll talk more about ASLR at a later stage. So if we can get that, any of those three primitives potentially could be possible. So I gave examples of reading and executing. And of course, you overrode it, so. UAFs are not always going to be exploitable. It's very, very much operating system, application, and allocator specific. What's true in one situation may be completely 100% different in another situation, so don't think it's true across the board. If you go online or in certain books and do readings on certain things, don't assume that it's going to be true in every situation. It's going to be very specific based on what you're dealing with. So lots of improvements and mitigations have been created to try to address it. But ultimately, the goal here is, we have a chunk of memory. It's been freed, and we have a new allocation of that size that occurs sometime shortly thereafter, and we will try to, if it's the same size, we'll place it there. One reason to do that is to prevent fragmentation of the heap and other issues as well. So that's just traditionally how it's done. How can we try to avoid that? As a programmer, you could try to use smart pointers instead of native pointers. That would be useful. Some other issues as well. Right here we can see a real-world example of how we can get this to work. So we have some HTML, and within that we have some JavaScript, and we have some allocations here. So a couple allocations of an object, and so somehow creating this object, we are overriding something. And then we get over into this loop condition here, that we get that to return if the G loop is equal to 2. Um, and I haven't studied this extensively, so some of this can be rather tricky, but this is happening here in JavaScript. But keep in mind that this is a browser. It's a process. It's dealing with virtual memory. It's dealing with the heap and all of that. So this is taking place on the heap. So there was a use after free, and now we have overwritten it with something. So we were able to be or this individual was able to be successful with the UAF. So don't worry too much about this. As we get a little bit deeper into the weeds, we can address some of this type of stuff, and it'll make a little bit more sense. So isolated heap was one mitigation that Internet Explorer Microsoft had to address that. So UAFs were very, very prevalent. They're having 150, 200 a year. And then about 2014, Internet Explorer, they try to address that with the isolated heap. So rather than having a process heap where all dynamic objects occur in Internet Explorer, we have the process heap for user-created objects, and then the critical Internet Explorer objects would go in the isolated heap. So things like what we had in the previous example now go into the isolated heap. So that helps. The idea was to prevent things, the user from being able to influence the things that were on the heap. But it turns out that that wasn't enough. So people still, even though it was a separate isolated heap for the critical Internet Explorer objects, people still could do much the same behavior where they could cause it and time it just right so that they could override it with something that would be malicious and help them. So isolated heap wasn't enough, so they added a second thing a few months later called deferred free. So that says anytime there was a call to heap free, it would redirect to protected free. So if you looked at it in IDA Pro, you would see that it's just now redirects to protected free. And what it does is it puts it on a hit list. So a hit list of, say, I don't know, 100 different things that are to be freed. And it'll all occur simultaneously. So what that does is we can't free something and then spray it with a few objects and hope that it's going to override it with an object of the same size, because we're going to have all these other objects that are going to all be freed simultaneously, some of them the same size, some of them in different sizes, so that overriding trick just doesn't work. Does that eradicate every possible UAF scenario on Internet Explorer? No, it does not, but it eradicates the vast majority of them. So that's all I have for us right now, and hope you enjoyed this slide presentation. On Thursday, we will dig a little bit deeper into fuzzing, learn a little bit about that. So fuzzing can be a great way for us to get some unexpected results. So we'll check that out, and I will chat with you then.